Thank you, Pravanji, and good afternoon, all. So my talk is about R&D digitalization, and when we talk about R&D digitalization, AI ML has become kind of buzzword, right? And often we get kind of questions like, all we need is AI, and do you have it in your software? And then follows with the common questions like how it can help in my day-to-day activities, how it can give me some scientific prediction, operational efficiency improvements. Answer to all those questions, yes, of course, AI can answer all those questions. But what is really missing? It's not AI, but the foundation for this AI, right? So what is missing is high quality standardized data, the context, integrated workflows, data governance that makes those results reliable, right? And it's a journey, which is like when we talk about AI-driven innovation, it's kind of journey that doesn't start really with AI algorithms, but it starts with your data. And it starts with a simple step, which is capturing all your scientific data, scientific knowledge digitally. And when it comes to chemical R&D particularly, that scientific knowledge begins with a molecule, right? And so the first step is to capture that molecule digitally. So where it's a chem draw, so you can capture that molecule digitally, whether it's a small molecule or a large molecule. Ensure there is a consistency in accuracy using standardized nomenclatures and representations so that scientists can communicate this chemistry more effectively with the chemical context. They can understand their properties and safety-related information about the molecules. And most importantly, by doing so, they create a digital language of the chemistry. So what it does, with using this kind of smiles and itchy strings, which creates machine-readable chemistry, okay, that makes it ready for AI, ML, and analytics, this kind of advanced possibilities. So now that molecules have moved from just from a sketch to digital chemistry, now the next important step is to connect these molecules with the physical assets, your physical materials, so that scientists can use it in their labs. And so it is, whether it's your starting material, your target molecule, various samples, reagents, chemicals, all those molecules needs to be connected to a physical assets, physical material, so that scientists can easily find those material, their locations. If it is not there, they can initiate order, request, they can communicate information about that materials. Once it is ordered in their inventory, they can track their batch lineage, container lineage, they can transfer the custody of those materials. All these operations can happen with chemistry context. In addition to that, having chemical structures brings that property predictions, the safety information, hazards, which is much needed in the planning phase. Right? So now that we have a chemical sketch which is transferred to the molecule, and then molecule has been connected to physical asset in materials, now it's ready for use in a lab. And when it goes to the lab, scientists can build a digital thread which connects together this chemical structure, the molecule, and the experimental execution. So they can look at entire process scheme, reactions, and so now what we have seen is converting that chemical sketch into a digital asset, connecting it with a molecule, materials, and making it ready for the execution. So when it comes to the execution part, where scientists can have access to those materials along with their structures, they can look at the scheme of the reaction, and they can have easy access to those materials. They can check, query that inventory, see what containers are available, they can move those containers as required. So scientists get clear visibility to the materials rather than relying on the stores, right? And they can further capture all their parameters, process conditions. From that, whatever product they have, the samples, again, they can associate structures with those samples and then follow the collaborative workflows, whether it's various test requests, sending it to different groups. So all this communication happens with a chemical context rather than going on different solutions like a notebook, inventories, and stores, or some drawing tool. Within a workflow, they can have all those pieces together, and it creates more connected science. But when it comes to process R&Ds or chemical plants, it's not just about one single experiment. When it comes to a particular process, it's like multiple workflows, hundreds of experiments, different documentation is required, and decision making is required at different stages. So it gets much more complex, and it's not only about making a connected workflow, but it requires enhanced coordination. It requires more orchestrated, automated workflows, and that's where having all this structured data can help them in closing these process gaps. So all these pieces can talk to each other. They can, let's assume the scientist performs the experiment. He can have easy access to the templates. It can create automatically experiment from that templates, fetch the materials that are required, highlight the safety hazards information associated with those materials. At different stages, it can compare with the criteria and assess the results, and that can make decisions. So that's how it can minimize the hands-off, minimize those gaps. It will build on existing knowledge and connect to the next steps. So that's how this orchestration can help. And then with all this data, it's not only about connecting data and having this orchestration. Finally, you would like to make use of this data, how you can access this data and make a decision. And that's where all this data needs to be unified. So that's where having all this data in a one system, scientists can push all their measurements, publish their measurements, experimental data, materials information, everything in one secure, trusted central repository where all your enterprise-wide knowledge will be captured, it will be standardized, indexed, it will be easily searchable. So having all this trusted data in one place, scientists can query required subset of data and visualize it in interactive dashboards. They can do advanced analytics to answer specific questions. For example, let's say some examples which I have put here. Let's say once the material goes from R&D to plant scale, what is more important is to understand the bottlenecks at each of the stage, understand the safety hazards, cost contributors. And so this is an example where you can see in one interactive dashboard, they can see what are the cost contributions by individual solvents, reagents, or labors, or bioreactor costs that are involved for each individual step as well as in overall production. So it gives more clarity. Also, it shows the cost by individual reagents, or is there any safety or hazards or risk associated with any of the materials so that they can corrective action in the right time. So that's how they can easily access all this information. Moreover, let's say they have multiple process routes, so they can have the side-by-side comparison of different process routes along with their key performance criteria, what is the atom economies and PMIs or yield efficiencies, so they can compare all those multiple processes. So having visibility, easy accessibility to all these analytics can help them in making better decision. They understand what are the trade-offs and make selection of optimum routes. So having this analytics gives answers to specific questions, and of course it gives more precise specific information, but what is more required is easy access to the knowledge. It's not only about the dashboards, and that's where scientists, everyone is using ChatGPT nowadays, and they want, okay, easy access to my knowledge. I would like to place a query in just a natural language, and it should fetch me the answers rather than going to the analytics dashboard. And this is some of the examples. Let's say I would like to see all the experiments that I have performed in this year so far. And I can ask this question, okay, give me the list of all the experiments and specifics about for which departments or disciplines I have performed those experiments. This AI can go back here, search my repository, go by experiments, notebooks, and all the experiments that I have created. It fetch a nice visual graphic showing me that all different departments where I have worked, how many experiments I have performed, and also giving me the summary. And I can further drill down. Let's say, if I have performed some work on a chemistry, give me more information about all the kind of reactions that I have performed and how is the success rate of those reactions. And I can further drill down and say, okay, so it gives me again deep dive into my data and gives answer that, okay, these many reactions you have run, this is a yield and success rate with all your reactions. It's not only what descriptive answers, but you can also deep dive, ask more, get more scientific insights. For example, further to that, I would like to know specific chemistries. Let's say, tell me all my Suzuki and Dalder reactions which I have performed so far, render all the reactants, show me all the bond formations or functional group transformations that have happened, and having this digital language of chemistry and all this knowledge together, what it does, it goes back, fetch all this information from all my hundreds of experiments, reads those chemistries, and bring this more science-specific information to me. And making it, that's how it makes much more easier to access the scientific data, your own trusted data. Now the question comes, okay, fine, it is showing me what already exists in my system, but how it can help me to innovate, create something new, whether it can suggest me some new experiments or what has never been developed before, but that should be based on my own trusted database, right? And that's where we are closely working with many of our partners to develop these AI-augmented design solutions. And this is one example where you can see on the left side, this is a chemical reaction recommendation. So it's a deep neural prediction models built on highly curated databases, reaction databases. Those models can help in suggesting reactions. So in this example, scientists just needs to input a rough idea, partial reaction, and once they enter the reaction, it can go back, this model can auto-map entire reaction, see what are the potential, what are the good catalysts, reagents, solvents, it provides those suggestions, and it's not software's decision, still scientist is the king who will decide. Scientists will see what are the catalysts are required, they will make the selection. As scientists make selection of those particular catalysts, reagent or conditions, it will dynamically change the reaction scheme and potential outcomes of the reactions. So that's where these prediction models can bring value in creating new schemes. On the right side, what you see is a traditional design, make, test, decide cycle. And this is a traditional approach, and as we all know, design is the most critical step, most time consuming, and this is the place where AI can make a dramatic impact, okay? And so this is where we are working with our partners, and what we have is the design cycle can be AI augmented. So with the predicted models embedded within the workflows, what it does, it build on your private as well as public databases and generate new molecules. So in the design phase, it can create novel molecules, predict their physical properties, do virtual screening before going to the physical labs. And with that, scientists can make a selection, and then they can perform this experiment, wet chemistry experiments, they perform all this analysis, and these results can go back again to that model to enrich that model. That model can relearn from that. So it's a repetitive cycles in which these models can learn and augment and give more intelligent, refined solutions. It can also be offered as a model as a service. So it's not just a software, not for one organization, but these models can be offered as a model as service shared with collaborators. So different collaborators, they can add their knowledge, they can contribute to this model, and that can lead, that can create a collective intelligence. It's not only for the one organization, but it will for the larger benefits. So what we have discussed so far, all these examples, possibilities I have shown you so far, are built on Revvity Signals platform and software solutions. And of course, this session is not about a specific applications or solutions. For example, how we support entire make, test, decide cycle using ChemDraw, which is our chemical drawing tool, or Signals notebook, or Signals One platform, or the data analytics capabilities which comes from Spotfire. So the objective is not about this, focus is not about the products, but more about the journey. So where it starts, the journey starts right from the molecule. So how from molecule to innovation, you can use all these digital platforms, and that can lead more collective intelligence. Okay. So these are some of the organizations we work with across the R&D spectrum in a different areas, and we are happy to discuss with you, connect with you during this event or after this. Thank you very much.